Here we'll talk about calculating combinations. So suppose we have determined that we need to use a combination in a particular question. And if this is something that you're trying to determine, the previous video talked about how to determine whether to use a combination or not, whether order matters or not. Here we're just going to talk about, suppose we've already determined, okay, order doesn't matter, it is a combination, how do we get the number? Here we're focusing on getting the actual number. Now I'll say that sometimes answer choices will be written in the form of, say, 5 choose 10. So we won't actually have to do the calculation, and that typically most happens when the combinations are very, very large. The test will just list answer choices in that form, something choose something, and we don't have to do any calculations. We simply have to recognize. More often, though, we do need to calculate combinations. First of all, remember that the formula, the way that it's set up, it looks like it requires a massive amount of calculation. There are 3 factorials there. If you ever make the mistake of calculating the 3 factorials separately, you'll be making the problem much, much harder for yourself. And so in that sense, the formula can be misleading. Using this formula is much more efficient if you remember that the larger factorial on the bottom, whichever one of those 2 is larger, will always cancel. That's always the way to begin using this formula. And so just as an example, I'm going to calculate that combination that I had on the first slide, 50 choose 10. Now this would be much larger than anything the test would expect you to calculate, but I'll show this just for the sake of an example. So first of all, plugging into the formula, we get 10 factorial, we get 50 factorial over 10 factorial times 40 factorial. Well, of the 2 factorials in the denominator, 40 is bigger. Now let's think about this. 40 factorial, that's the product of all the numbers from 40 down to 1. 50 factorial is the product of all the numbers from 50 down to 1. Well, included in that, we'd go from 50 down to 41, and then starting at 40, it would be 40 factorial. And so 40 factorial immediately cancels. And so what we get once we cancel 40 factorial, we get all the numbers from 50 down to 41. Everything below 41 has canceled, so that's left in the numerator. And in the denominator, we're just left with 10 factorial. And now we're going to do a little more cancellation. And so basically, you want to cancel as much as possible before you do anything else when you're using this formula. In other videos, we've talked about cancel before you multiply as an important rule. Here it is a paramount rule. You have to cancel before you start multiplying. So first of all, we can just cancel the 50 with the 5 and the 10 in the denominator. Then we can cancel the 42 with the 6 and the 7. Then the 8 times 3 times 2, or 8 times 6, that cancels 48. We'll divide 45 by 9, leaving us with 5. We'll divide 44 by 4, leaving us with 11. Now we could rearrange the order of those factors, but basically the test might expect you to simplify down to that. Now, no one is going to expect you to come up with this answer here. That's the actual answer when we multiply everything out. So this is just an example of how to cancel. And again, this is a much, much bigger one than anyone would expect you to calculate. The approach we have recommended in previous videos is much more efficient. Begin with the fundamental counting principle and then divide to eliminate repetitions. Remember to cancel before you multiply. Remember to leave all products unmultiplied until all possible canceling is done. I will also show a couple other ways to think about calculating combinations. One shortcut involves the case of n choose 2. That is a case in which we are picking an unordered pair from a larger set. Let's think about this with the fundamental counting principle approach. We have n choices for the first item and then n minus 1 choices for the second item, but because order doesn't matter, we have to divide this product by 2 because each pair would be counted twice. And so we get n choose 2 equals n times n minus 1 over 2. And that's just a handy formula to know. You may remember from the sum of sequence videos that this is also the sum of the first n-1 positive integers. It's worth remembering that this shortcut pattern shows up in a couple different areas of mathematics. And if you haven't seen that video, that would be a helpful video to watch, and it might help you remember this as well. Another mathematical pattern that is directly related to n choose r is Pascal's Triangle, named for Blaise Pascal. And so here's Pascal's Triangle. It's often something that they have little kids create because everything is just created by addition. If you notice, every number is the sum of the two numbers diagonally above it. For example, 3 is 2 plus 1. 6 is 3 plus 3. 4 is 3 plus 1. 10 is 6 plus 4, etc. Once you have any row across, it's very easy to find all the rows underneath it. So the two outside diagonals are always the ones, and again, all the inside numbers are the sum of the two numbers diagonally above it. Pascal's triangle gives all the values of n choose r. In fact, n choose r is the entry in the nth row at the rth place in Pascal's triangle. The tricky thing about this is we need to remember to start counting rows and places from 0. The top one is the 0th row, 0 place. 0 choose 0 equals 1, but that's not very meaningful in real world combinations. You know, you have nothing. How many different ways can you pick nothing? I guess, you'd have one way of picking nothing, It's not very meaningful. In any row below the first one, the second number in the row gives you the row number. It's often a very good shortcut to have row 3 memorized. So 1, 3, 3, 1. That's a really good place to start. It's a good starting place. And from there, we can generate several more rows very easily. So for the fourth row, we have the ones on the outside. 3 plus 1 is 4. And of course, that doesn't surprise us because we have to have 4 as the second number in the fourth row. And of course, it's symmetrical. It's 100% symmetrical. So when we add it on both sides. And then, of course, 3 plus 3 is 6. So now we have the fourth row. Now we can get the fifth row. 1's on the outside. 1 plus 4 is 5 on both ends. 4 plus 6 is 10. So we get two 10s in the middle. Now we can get the sixth row. 1's on the outside. Then we get 6's. Then 5 plus 10, 15. And then in the middle, 10 plus 10 is 20. Now the seventh row, we have 1's on the outside. 1 plus 6 is 7. 6 plus 15 is 21. And 15 plus 20 is 35. So we'll stop there, but let's see what we have now. This is the seventh row of Pascal's triangle. Well, the first entry, 7 choose 0 is 1, is not very interesting. If you have 7 things and you choose none of them, how many ways can you do that? That's not interesting in real world terms. Then, of course, 7 choose 1 is 7. If we have 7 unique items, how many different ways could I pick one unique item? Well, 7 of them. But then the meaningful combinations, 7 choose 2 is 21, 7 choose 3 is 35, 7 choose 4 is 35, 7 choose 5 is 21, 7 choose 6 is 7, and of course 7 choose 7 is 1. And so we get all of those numbers all at once, all the way across the row. And you can see if you had a problem where you had to compute 7 choose 2 and 7 choose 3 and say 7 choose 5, if you had to compute all these numbers, it might just be easier to calculate the row of Pascal's triangle, and then you have all of these numbers automatically. If you practice constructing Pascal's triangle, you'll get quick at it. And again, this is something they have kids in grade school do, so it's not actually very hard to create Pascal's triangle. And so if you practice it, especially start with row 3 and practice it, you can get very, very quick. Then you can just jot it down at the beginning of the quant section, and you'll just have it if you need it. If in a problem you have to figure out different size combinations from the same pool, say 8 choose 3 and 8 choose 4, then it may be quicker to draw Pascal's triangle down to that row rather than to do all the separate calculations. In summary, remember that you can always calculate combinations by using the fundamental counting principle and dividing to eliminate the repetitions. Remember to cancel in the n choose r formula, including canceling before you multiply. Remember the shortcut formula, which also appears in sums of sequences, and practice using Pascal's triangle to generate values of n choose r.